Good morning, students. Today we can discuss about Gauss's theorem and its applications. Again, very important side of our first chapter, the last topic of the first chapter, very important one. So listen all of you. Okay, Gauss's theorem. Now, as per Gauss's theorem, it gives a relation connecting the flex enclosed by a closed surface with the charge enclosed. Do you understand what I said? Flex with charge. It gives a relation connecting electric flex with the charge enclosed. Okay. As we all know, what is the equation for flex, or what is the representing letter for flex? It is phi. Now, as per Gauss's law, the electric flex enclosed by a closed surface is 1 by epsilon 0 times the charge enclosed by the surface. 1 by epsilon 0 times the charge enclosed by the surface. That means the flex depends only on the charge present inside the surface. Okay, so this is the statement of Gauss's law. Very important one. From the mathematical side, we can define it. What is it? The total electric flux over a closed surface is 1 by epsilon 0 times the net charge enclosed by the surface. Now, coming to its mathematical proof, how can we prove this? Okay. Now, for that, we have to imagine a spherical surface just like a ball with a charge q at its center, just like this. Okay. So, imagine a spherical surface with a charge q at the center of the sphere. Let r be the radius of the sphere. Okay. Now, how will you prove an equation? You have to start from LHS and you have to arrive at the RHS. Okay. Now, what is our left side of the equation? Phi. So, you have to start from phi and you have to arrive at this result. Okay. Let me see how can we prove this Gauss's law. Okay. What is the left side of our equation? Phi. Phi equals. Can anyone say what is the equation for electric flux that we have already studied? What is the equation for flux? Equation for electric flux is surface integral E dot ds. Here E is the electric field vector and ds is the area vector. So we have to calculate the total flux over this spherical surface. Now how will you find the total flux? Now in order to find the total flux, you have to divide the entire surface into small surfaces, and you have to calculate the small flux across such surfaces, and you have to add it. That is the procedure. Okay. Now for that, in mathematics, we will do the process of integration. Clear? Now I am dividing the whole surface into small portions, and I am taking one such portion and its area is ds, and the direction of area is always normal to the surface, and let ds be the direction of area. Okay. Now here the charge is positive. The direction of electric field due to this positive charge, it is also in the outward direction. That means we can see from the figure both the field and the ds, they are along the same direction. Okay. So first we can find what is the flux over this small ds or the small portion ds. Okay. Now that small flux d phi, I can write it as, what is that small d phi is equal to E ds. Is it right? How this dot becomes? Because actually it is E ds cos theta. Now here the angle is 0. So cos 0 becomes 1. So it becomes E ds. Okay. Now we have to find the total flux. Now what is the procedure for doing or finding the total electric flux? You have to integrate d phi. Now phi equals integral d phi. Okay. On integration, we can substitute d phi as E ds. Clear? Now, you can take E outside from the integral, so you will get E into integral ds. Clear? Now, what is the integral of ds? Integrating ds means we are summing the total surface. So, on summing, you will get E into S. Here S indicates the total surface area of the sphere. Now what is the total surface area of a sphere? It is 4 pi r square, and also we know that at each and every point on the surface the magnitude of electric field is same. What is it? It is 1 by 4 pi epsilon 0 q by r square. That means you can give E as 1 by 4 pi epsilon 0 into q by r square into S. What is S? The surface area of a sphere is 4 pi r square. So that we can cancel 4 pi You can cancel r square. So the remaining term is, what is the remaining term? Phi equals 1 by epsilon 0. 1 by epsilon 0 into q. So this is the final expression for the flux. That is our RHS, right? Hence we proved Gauss theorem. Do you understand? It's very important topic. Students, now we can explain the applications of Gauss's law. As we have already discussed, Gauss law is giving a relation connecting the flux with charge. Whereas in the case of application, we are using Gauss law to find electric field. So it is a very important point. We are using Gauss law to find electric field. Mainly there are 3 applications due to 3 different charged systems. The first application is we are going to find electric field due to a charged wire, infinitely long charged wire. That was the first application of Gauss law, that is electric field due to an infinitely long charged wire. Now what do you mean by charged wire? Means a wire in which the charges are distributed uniformly. So I am assuming an infinitely long wire, though the charges are distributed uniformly. And we have to find the electric field at a point outside the charged wire. We have to find electric field by applying Gauss law. Okay. Now the very important point is that in order to apply Gauss law, we need a closed surface. Now here our system is a charged lengthy wire. Here we have to imagine a closed surface as, or Gaussian surface as, the cylindrical surface. So cylindrical surface is the Gaussian surface here. Okay. Now by applying Gauss law, we have to find the electric field. Now for that, we can divide this cylindrical surface into 3 regions, 1, 2 and 3. Here these first and third regions are the circular faces of the cylinder, and the second region is the curved portion of the cylinder. Okay. Now we have to find the flux enclosed by the Gaussian surface, and by applying Gauss law, we have to derive electric field. We have to find an expression for electric field. Okay. Now coming to the first region, the first circular face, there the area vector and the electric field, they are in the perpendicular direction. Okay, because here the charges are positive, the direction of electric field is outward, so the angle between E and ds is 90 degree. Now what is the flux over here? Phi is equal to E dot ds. E ds cos 90. Cos 90 will be 0. Clear? That means there is no flux over here. Now what about the flux at the third region? Here also E and ds are perpendicular. Here the flux also 0. That means in this case, the flux is contributed only by the curved portion of the cylinder, curved surface. Okay. Now, by applying Gauss law, we can write the first equation as phi equals 1 by epsilon 0 into q and mark this equation as 1. Now, you have to find flux separately, then you have to find charge separately, then you have to give substitution in the first equation. Clear? Okay, first we can find flux. Now, we know that the flux is contributed only by which surface? The curved surface. So, we can write the equation for phi as surface integral E dot ds. Clear? Now, coming to the curved surface, tell me what about the direction of electric field and area vector along the curved portion? Both field and ds, they are along the same direction. That means the angle between them is 0. So that E dot ds becomes E ds cos 0. Cos 0 is 1. So that you will get E dot ds becomes E ds. Okay. Now our aim is to find electric field so that we can take E outside, integral ds. Now on integration, ds becomes S. Now here S indicates what? The curved surface area of the cylinder. Tell me what is the curved surface area of the cylinder? It is 2 pi RL. So we got the second equation as E into 2 pi RL. Clear? Now next our aim is to find Q. Already I explained here the charges are distributed uniformly over the length of the wire. So here you have to take linear charge density lambda. That means linear charge distribution we have to consider, and the linear charge density lambda can be written as the total charge distributed divided by the total length. Now from this we can get the equation for Q as lambda L. Okay. Now by substituting the third equation as well as the second equation in the first equation, you will get E into 2 pi RL equals 1 by epsilon 0 into Q. Instead of Q you can give lambda L. You can cancel L on both sides, and our aim is to find again what? Electric field. So electric field E equals lambda divided by 2 pi epsilon 0 R. Out of this, lambda is a linear charge density which is a constant, 2 pi is a constant, epsilon 0 is a constant. That means the field depends only on R. Is it directly on R or inversely on R? Electric field depends inversely on R. That means as distance from the wire increases, the field decreases. Coming to the second application of Gauss theorem. Again we are going to find the electric field, but here the system is a charged sheet. Okay. So let this be a charged sheet, and due to this charged sheet we have to find electric field at a point outside the sheet. Okay. Now to apply Gauss' law, we need to imagine a closed surface. So here also our closed surface, Gaussian surface, is the cylindrical surface that is piercing through the sheet. Okay. So this cylindrical surface is piercing through the sheet. Now by applying Gauss' law, our aim is to find electric field. So as the first step, you have to find the electric flux enclosed by this cylindrical surface. Same as before, here also we can divide our cylindrical surface into 3 regions. First region is the first circular face, the second region is the curved surface, and the third region is the third circular face. Now we can see from the circular faces, the surface area S and the electric field due to this charged sheet both are in the same direction. That means there exists maximum flux over this circular portion, and that maximum flux will be E dot ds or E ds. On integration it becomes E into S. That means the flux over here is ES. And also at the next circular face, here also the total flux is ES, because the S and the electric field, they are along the same direction. So here also the flux is ES. Okay. Now what about the curved portion? Along the curved portion, area vector is perpendicular to the surface and electric field is towards left. That means the angle between them is 90 degree. That means the flux is 0. That means the curved portion is not contributing any flux. So the flux is contributed only by the 2 circular faces, and that total flux we can write it as ES plus ES, that will be twice ES. Okay. Now coming to the mathematical side, by Gauss' law, phi equals 1 by epsilon 0 into Q, mark the equation as 1. Now LHS, we are calculating the flux first. Already I explained that flux is twice ES, equation 2. Okay. Now we have to find the charge Q in the RHS. Now here we know that the charged system is a charged wire. The charges are distributed entirely over its surface. So which charge distribution we have to consider? We have to consider the surface charge distribution. And the surface charge density sigma can be written as Q by area. Area here it is surface area S. So that Q becomes sigma into S. So we got both Q as well as flux. Now substitute in the first equation, so that you will get 2ES is equal to 1 by epsilon 0 into sigma S. Cancel S on both sides, so that you will get electric field E equals sigma by 2 epsilon 0. That means sigma is a constant, epsilon 0 is a constant. That means the field due to a charged sheet is always a constant. It doesn't depend on the distance. Coming to the last application of Gauss's law, that is, here we have to find the electric field due to a charged shell. So the first one is charged wire, second one is charged sheet, and the third one is charged shell. So here this small sphere is the shell, where the charges are distributed entirely over its surface, and its radius is capital R. Okay. Now we have to find the electric field at a point outside the shell first. Now in order to apply Gauss' law, here also we need to imagine a closed surface, And since our shell is spherical in shape, here we can imagine a closed spherical surface as the Gaussian surface. Clear? Now the radius of our spherical Gaussian surface is small r and the radius of our shell is capital R. Okay. Now by applying Gauss's law, we can write the equation as phi equals 1 by epsilon 0 into q. Same as before, we have to first find the flex, then we have to find the charge, then you can do the substitution. So first our aim is to find the flex enclosed by the closed Gaussian surface, that is the spherical surface. Now what is the equation for flex? Phi equals surface integral E dot ds. Now tell me, what is the angle between electric field and area vector here? Because these charges are positive, the direction of electric field is outward and the area is also along the same direction. That means electric field and area are along the same direction. E dot ds becomes EDS. Okay. Now on integrating, ds becomes S. So you will get the flex as ES. Clear? Now tell me, what is the surface area of that Gaussian spherical surface? Since its radius is small r, we can write it as E into 4 pi r square. Okay? Mark this equation as 2. Now we need equation for charge. Same as before, here also the charges are distributed over the surface of the shell. So which charge distribution we have to consider? We have to consider the surface charge distribution. And the surface charge density sigma can be written as Q by surface area. Here this S indicates what? Here this S indicates the surface area of the shell. What is the surface area of the shell? It is 4 pi r square. Now from this, what is Q? On cross multiplying, you will get Q as sigma into 4 pi r square. This is our third equation. Now you have to substitute the second and third equation in the first equation, so that our equation becomes, instead of phi you can give E into 4 pi r square, and which is equal to 1 by epsilon 0 into, instead of Q you can give sigma into 4 pi r square. Cancelling the terms 4 pi on both sides, you will get electric field E as sigma by epsilon 0 capital R square by small r square. This is the final expression for electric field at a point outside the shell. Clear? Now, what about the electric field if the point P is on the surface of the shell? If the P is on the shell. If the P is on the shell, our Gaussian surface as well as our shell both are same. That means the small r is equal to capital R. So we can cancel small r and capital R, so that you will get the equation E as sigma by epsilon 0. Right? Now you have to find the field inside the shell. Inside the shell means you have to take the point P inside and you have to imagine a closed Gaussian surface inside the shell. Now tell me, is there any charge enclosed by the Gaussian surface here? No, because the charges are residing over the surface of the shell. So there is no charge enclosed by the Gaussian surface if you are taking a point P inside the shell. So if the charge Q is 0, then we can say phi is 0, right? Phi is 0 means surface integral E dot ds is equal to 0. Area will never be 0. So the only possibility is electric field should be 0. Clear? That means within the shell, electric field is 0. So these are the three cases. Do you understand? Outside the shell, on the shell and inside the shell. Okay? That's all. Thank you.